Only in physics does it seem like you can be intimately familiar with something that you just don't understand at all. You can encounter a concept so many times to where you feel like you must get it, and then you're immediately humbled trying to explain it to an undergrad. I think one such concept are moments of distributions. You may know how to calculate the moment of inertia about some axis, but then you're looking at your calculation like a parent looking at their kid's artwork. Great! What is it? Now this mini-series is all about teaching you to fish. I'm not going to be providing you with a comprehensive list of moments in physics and how to interpret them, but rather I'm going to go over the procedure that I use that generally makes interpreting moments of distributions much easier. In this video we'll be focusing on how moments are defined statistically, and we'll spend a good amount of time going over the math that we'll be using throughout this series. In the second video, we'll turn our attention to moments of an actual physical distribution, a mass density, and see if we can connect the dots back to this video to come up with some statistical interpretations of things like the moment of inertia. In the third and final video, we'll look at moments of a charge distribution as our final example. In other words, how do things change when our distribution is no longer necessarily positive definite? Charge can be negative, but probability can't be negative, and we'll see how to connect the dots back to statistics there. Now there's a lot we can talk about with moments of charge distributions, so I'd really like your feedback over these next couple of videos to help me decide how much to include in that third and final video. But for now, let's get started with a mathematical primer on an object we're going to be using extensively throughout this mini-series, the Dirac delta function. Now, if you're a physics student, eventually you're going to need to learn how to describe densities of point-like particles. So say the charge density of a point particle or its mass density of a point particle. And in order to do that, we're going to have to introduce ourselves to a new friend, or it might be an old friend for some of you. A new friend. And our friend is going to be called the Dirac delta function. And some people are already commenting how it's a distribution, not a function, or sometimes you'll hear it referred to as a generalized function. But why do we need to define this new object in order to describe point-like distributions? Well, if we take, say, something like a mass density, so say we have the density at some point in space of an object, for a point particle, well, we know something about a mass density would be something like the total mass divided by the volume that it occupies. Well, for one, what's the volume occupied by a point particle? It's zero. So, but it's also not constant, right? The density of a point particle isn't constant. If I put a little point particle right here of some mass m, and it's located in space x equal to a, y equal to b, z equal to c. Okay, well then I'm specifically saying that there's mass here, but there's not any mass over here. So the density shouldn't be constant. It's all concentrated at this point, or the mass is smeared over this mathematical point at ABC. But we also know that point particles occupy infinitesimal volumes, so at the point where there is mass, the density is formally infinite. So it's zero everywhere else, and like infinite at that point. So we need some weird kind of object to pick up that infinite behavior of the point-like particle density. And the object that's going to do the trick is called the Dirac delta function. I didn't mean to do that. So it's typically denoted as a delta of x minus a, if we're working with a one-dimensional delta function. In this case, we have a three-dimensional particle that's located in three-dimensional space, so we'll figure out how to describe it in 3 dimensions. But for now, the one-dimensional delta function centered at a is defined to be formally infinite for x equal to a, and it's 0 at x not equal to a. So if we were to plot this out real quick, roughly, here's delta of x minus a, x-axis is just x, and let's put a here. Then delta of x minus a looks something like this. It's 0 everywhere, infinite at the point, 0 everywhere else. Now what else do we know about densities? Well, when you integrate the density, you should get the physical thing, right? If you integrate a mass density, you should get the total mass at the end, if you integrate over space. If you integrate a charge density over space, you should get the total charge. So this delta function needs to have properties that allow that to be extractable from the charge, or from the specific density. So it's going to satisfy a few properties that we're going to outline. So some properties, there's a lot of cool things you can do with delta functions. This is not going to be a comprehensive review of them, but we're going to go over what we're going to need. And if you haven't seen these before, you'll see them in an introductory course in electromagnetism if you use Griffith C&M. That tends to be the first time that you see this. So some properties, and these properties are not going to be unrelated, is that sometimes you'll hear delta functions referred to as integrals waiting to happen. They really only make sense under an integral. So one property is that the integral of the delta function, x minus a dx, from minus infinity to infinity, is normalized to 1. So what this is saying is that even though at a the delta function is infinitely high, it's also infinitely thin, such that or infinitesimally thin, such that the integral gives 1. Okay. Now, in reality, maybe x isn't really defined from negative infinity to infinity. The real property that matters is not that the integral from negative infinity to infinity is 1, but really that the integral over this wrinkle, over where that divergent behavior happens, is 1. So in principle, we don't really need to integrate from minus infinity to infinity. We just have to integrate from a minus epsilon, where epsilon is some small number, to a plus epsilon, and then this is guaranteed to be satisfied. There's a there's a stronger property that's more general, I should say, that involves integrating the delta function against another function. So if we have some other function, say f of x, delta x minus a, this just picks out the value of the function evaluated at x equal to a. So it's just going to give you the number. So though we're introducing ourselves to this new object to describe something that's supposed to be simple, the simplicity is contained in how we use the delta function. It always makes integration easier. Now, for some intuition for why this identity ends up being satisfied is if we think about multiplying this delta function by some other function, let's say that this is f of x, then we're effectively multiplying f of x times 0 everywhere except for at that point x equal to a. So that's why it only gets a contribution at x equal to a. Now this is all a little abstract. Let's do a quick example. I promised you that using delta functions makes integration pretty easy, or I should say where they show up, integrals become easy. So if we do a quick little example, if I wanted to integrate e to the minus x over x squared plus the log of x times delta of x minus a, integrated over x, I just evaluate the function at a. This is e to the minus a over a squared plus ln of a. Really simple to use these. One thing that I should mention, from the first identity we can kind of see this, from the first property, well, 1 is dimensionless. It doesn't have units attached to it. dx, maybe we're integrating over distance as an example. Well, if we're going to end up with something that is dimensionless, that means that the delta function must have units that are inverse to the integration measure. In this case, inverse to dx. So if dx is a length, then delta of x has units of 1 over length. And if we're describing something's position in a three-dimensional space, we're going to have one delta function for each coordinate. So if we have a product of 3 delta functions, that's going to be the same if I have, say, you may see it denoted as d3r. Let's say minus a vector. d3r. This would be a three-dimensional delta function which you could unpack in the following way. It would be a delta of x minus some a sub x, delta of y minus a sub y, delta of z minus a sub z, dx, dy, dz. And again, if dx, dy, dz are really if the measure has units of distance cubed, then the delta function, this three-dimensional delta function, has units of 1 over distance cubed, or 1 over volume. So it really is going to allow us to pick up that infinite property of the densities of point particles, because it really is something of a density itself. In other coordinate systems, you would just have to know how your Jacobian changes. There are other relationships that will allow you to express delta functions in different coordinate systems, but we're not going to be doing that here. Just to make things painfully clear though, let's go ahead and start with our original mass particle. Actually, let's do two masses, just so things are clear. We'll have M1 at some A, B, C, and we're going to have another mass, M2, located over at, I don't know, D, E, F. So if I wanted to describe this mass density, I'm just going to use superposition of different mass densities, the density of this plus the density here. And the delta functions are going to keep tabs on where that mass is exactly located. Now, in general, yeah, A, B, and C, the position could depend on time. Maybe the charge is moving around or the mass is moving around. Again, for simplicity, let's curb that. We're just nailing it to the board. So the mass density in this example, M, or rho, I'm going to call all of my densities rho. Rho of R is equal to, it's going to be M1 times delta of all of the coordinates. So it's at x minus a, delta of y minus b, delta of z minus c, plus m2, x minus d, delta y minus e, and delta of z minus f. So that's how I would represent this point particle mass distribution, or this collection of 2 point particles, as an example. And because of the properties of the delta function, like if you're just integrating it, you get 1, then when we integrate this guy, we just get the total mass of the particle as we would expect. But we're going to see more of that in a little bit. Okay, so I hope that provides you with basic procedural understanding of how to use delta functions, and maybe makes more sense why they're such a good candidate for describing point-like particle densities. If it doesn't, we're going to get a lot more practice out of it, so I hope we'll start to build the intuition as we go. But for now, let's note that we're talking about moments of physical distributions at the end of the day, or at least we'll get to that. And we need to acknowledge that first and foremost, moments are a borrowed concept from statistics. Everything else that I say for the future of this mini-series, we're going to be trying to connect the dots back to this section on statistics. Statistics is going to provide us with very useful interpretations of moments of distributions, so long as we know what the distribution itself represents, what the variable we're integrating over represents, and what we're centering it on. And all this stuff hopefully will become clear as we get into it. So a borrowed concept. Okay. I think a good place to start with our statistical primer is highlighting the difference between moments of number densities and moments of probability densities. So we're going to start with a number density. It can be, say, the number of students who got a particular grade in a class. Now, some of you might think immediately, that's not a density. You're specifying the grade. You're not giving a range of grades. Usually, a density has like the quantity divided by some range of x, some width, the number of students who got between a 75 and an 80. That would be a density. If you're specifying a particular point, usually they won't call that a density unless you're using delta functions, because we can say that that is a density where the window is infinitesimally thin. And that's going to allow us to always be using integrals instead of going back and forth between integrals and summations. So let's go ahead and start with a number density. That we're still going to call rho. So we're going to have some ordered pair that I'm going to provide you with. And it's going to be some x and some rho of x, where rho is our number density. And this is going to be a grade. So the x values are going to be a particular grade. And the rho of x values, the y values, are going to be the number of students with that grade. Okay, so if we want to come up with some artificial data, let's say that we have someone got a 50%, that was me, someone got a 75%, let's say 2 people got a 75, and one of you who's watching got a 90. And I'm just going to start, I'm going to plot what this looks like. So if I want to plot rho of x, so function of x. I'm going to have data point at 50. Let's say that's where 50 is. Here's 90. And 75 would be somewhere over here. And the corresponding y values are just going to be either 1 or 2, right? It's going to be, we say this is 1, here's 2. And so our data is going to look like this. One person who got a 50, 2 people who got a 75, and 1 person who got a 90. Okay, so we have these discrete data points. It's not a continuous function. Hence why delta functions are useful. Okay, so what I first want to start by doing is writing out, can I write out a functional form for rho of x using delta functions? So we want to parameterize exactly where the grade is. So at 50, at 75, and 90, that's what we're using delta functions for. And then we're going to weight that by the number, how many students got it. So rho of x in this case is equal to, well, we got one person who got a 50, so it's centered at x minus 50. And then we got, plus, we're just using superposition, plus 2 times delta of x minus 75, and plus 1, and these ones are just being multiplied. I just wanted to be clear what I'm doing. Delta of x minus 90, and this defines, this is how we can represent this discrete number density in terms of an actual function, or a generalized function, if you will. So this is what we're going to take as our number density, and I'm just going to start by integrating this. We know how to integrate delta functions now. So the integral of rho of x with respect to x is equal to, well, I don't have any other functions multiplying this. First of all, when I integrate this, I can just split it into 3 integrals, right? The integral of the sum of the 3 is equal to the sum of the integrals. I also noticed that this function, or this delta function, isn't multiplying any other f of x, or if you like, it's multiplying f of x, where f of x is just 1. So these things all integrate trivially. We know they integrate to 1. So when we integrate these delta functions, let's not be lazy. I was tempted to be lazy. Let's just, for clarity, because I am not smart enough to be lazy and I will make a mistake, and then you guys will pay the consequences. Okay, dx. So the first integral, well, actually all of these integrals just give 1, right? Integrating this gives 1, integrating this gives 2 times 1, and integrating this gives 1 again. So when we integrate this function, it gives 1 plus 2 plus 1, that's 4. Wow! 4, right? Very exciting. Well, no, what does 4 mean? What is 4? Well, 4 is just the number of students who's in the class. And integrals of this form are referred to as zeroth moments of the distribution. So, zeroth moment of rho is defined to be the integral of rho of x dx, or if it's multivariable, we'll integrate over all of the variables. Depending on what our distribution itself represents, changes the interpretation of the zeroth moment. The definition is always the same, but the value depends. This is always true, but whether it's always the sum of parts, like in this case it was n, the total number of students. If we did it with a mass distribution, we would get the total mass. For charge, it would be total charge. You get the idea. But what if we changed our distribution to be a different kind? Like what if we took this, I'm going to just copy and paste, and I'm just going to divide, I'm going to draw out another distribution where I'm just going to take the original one and divide by n. Then, if I just copy and paste again, all I'm saying here in this yellow arrow is that we're taking the y values and dividing by n, or dividing by 4. So this 1 and 2 becomes a 1/4 and a 2/4 respectively. 1/4 and 2/4. Okay, well if we know that when we integrate rho of x dx here, that gave us n. And if we integrate this one, this new rho of x, so rho of x over n, that just gives us 1. So the normalization of our distribution kind of changes the interpretation. Here we have a number density. The value at this point, this is, like I said, we're saying one person got a 50%. This one is actually a probability density. This is saying if I randomly sample one person out of my 4 students, then there is a 1 in 4 chance that the student I select will have gotten a 50%. So in this case, the integral here gives you the sum of parts. The integral of this distribution, rho of x over n, that just says that the probability that a student got a grade is 100%. So the interpretation of the 0th moment changes depending on if the moment is normalized. And in physics, sometimes it can't be normalized. So what we're going to be doing is we're going to be working with non-normalized distributions unless I explicitly say. That way we can avoid this confusion. Okay, so 0th of rho, yeah, thanks, that's helpful. 0th moment. 0th moment of rho. Okay, what makes it a 0th moment? What makes it a 0th moment is you can think of there being an x to the 0th power multiplying this distribution, and we can define higher order moments by taking higher order powers of x. However, we're free to take moments relative to any reference point that we see fit. They're not always going to have the same interpretation, right? If you take the moment of inertia about one axis, that's going to be different than the moment of inertia about another. So what exactly we're inserting extra powers of will change the interpretation as well. But usually what tends to be the most helpful is talking about moments about the average as opposed to the origin. Nevertheless, the 0th and the first moment tend to be relative to the origin. And if this doesn't make sense, it will. So what we're going to do now is we're just going to sandwich an extra factor of x in here. So we're going to do the integral of x times rho of x dx. And this is going to give us, this defines what's referred to as the unnormalized. This is what I'm calling it. This is what I would assume other physics people would call it, but mathematicians will tend to normalize it already. Unnormalized first raw moment of mass, or of raw moment of rho. That's the technical way of saying this. We'll talk about raw means we're talking about this relative to the origin. If you do it relative to the average, they will call it a central moment. You can keep it relative to any point and they'll call it something else. To me, that I don't like doing that. That kind of reminds me of saying one thing for a Taylor series and then calling it a Maclaurin series when you center it at a equal to 0. Like, no one actually does that, but maybe it is instructive to keep the terminology clear here, so I will use it for this video. But like I said, we're going to be using unnormalized distributions unless explicitly said otherwise. So let's go ahead and integrate this. So if we integrate x times our original distribution, let's see if we can pick up some kind of interpretation. Spoiler alert, we won't immediately. The normalized version tends to be easier to interpret statistically. But we'll get to that. So right now we're just integrating. Now we actually do have a function f of x that's multiplying the delta functions, but it's just x. So it's just going to pick out the values for x equal to where the delta function is centered. So if we integrate this guy, dx, then we have, this is going to pick out, this integral is going to pick out x equal to 50. This one's going to pick out x equal to 75. And then the third one is going to pick out x equal to 90. And that's just what we're going to evaluate the x at, f of a, right? So this just gives, well, we have to remember the constant multiples out front. So it's going to be 75 plus 2 times, 50 plus 2 times 75 plus 90, which just gives us 290. Great. Again, what is 290? It's the total number of points allotted in the class. That might be useful information, but I think I'll convince you that the normalized version is typically, like I said, easier and more useful to interpret. So what we're going to do is we're going to take the normalized, or the first moment normalized to the 0th. We're going to evaluate x rho of x dx divided by the integral of rho of x dx. Those of you who've had some thermodynamics, this is maybe seeming a little similar now, or a little familiar. I think if you're taking moments like of the Maxwell-Boltzmann speed distribution. Well, these integrals we've already done. We don't have to reinvent the wheel. This gives us 290, and the denominator was the total number, which was just 4. So the ratio of these two moments, or the normalized first raw moment, gives us 72.5. And what is that? That, my friends, is finally something maybe a little bit more useful. It's the average grade. We've got one person who got a 50, two people who got a 75, and one person who got a 90. The average is going to be a 72.5. It's not the average y value. It's something like a weighted average of the x values, okay, where it's weighted by that density. So it's a weighted sum, if you like. So when we go to physics and we start taking, say, first moments of distributions, we'll have in the back of our mind that it will be related to an average of sorts, but an average in terms of the x, not of the y. So we're going to keep that in our back pockets. Maybe it's probably good to write up some punchlines so far before we move on, because we're going to stop. We're going to look at the second moment when we'll define the nth moment, and we'll pretty much just wrap up there. But let's go ahead and outline some punchlines so far. One, we know again that delta functions, delta of x, allow us to represent discrete I think there's 4 E's in discrete data continuously. And this allows us to replace summations with integrals, so we don't have to go back and forth. Sometimes we'll have continuous distributions, sometimes we'll have point sources. This way, it doesn't matter. We can always do integrals. The second punchline is that the 0th moment, so we have a 0th moment that's defined in terms of the integral of the density you're looking at, and understanding what the density represents itself is incredibly important to assigning any kind of interpretation to moments of the distribution. You can't interpret the moments if you can't interpret the distribution. That's why the first case gave us n as sum of parts, and the second case gave us 1, and we had to know what the distribution meant before we understood what that was telling us. But unnormalized, it represents a sum of parts. I'm going to keep saying that. 3, first, I'm going to call it a raw moment. Involves the integral of rho of x times x dx. So this is just a definition. And if we normalize it, it gives us an average. Okay. Okay, now that we've caught our breath, caught our breath, let's go ahead and move on. So I'm using the word raw moment, which I haven't really made clear what that means. When we take, say, the nth moment of a distribution, we're free to define a reference point anywhere we like. Once we go to mass distributions, this is akin to saying, what's the moment of inertia about the z-axis, or about the x-axis, or about some other point in space? We're free to make that choice, and that choice that we make changes things, right? The moment of inertia about the z-axis may not be different about the y-axis, but we want to be able to interpret what that difference tells us. We can define the nth moment in general, as defined as we insert our factor of x, our independent variable, but we can center this at any point that we want. I'm going to call it a, and the nth moment is then x minus a to the nth power times that original distribution integrated over all of the relevant variables. What makes it a raw moment means a is 0. It's a moment about the origin. A central moment takes a equal to mu, equal to the average. So the 0th and the first moment are all raw moments. The first raw moment defines the average that we can then use in the future central moments. So to put a little meat on this, what I'm saying, if we talk about a second central moment as an example, if we talk about M2, where a is equal to mu, then that defines, and we're going to go ahead and normalize this actually, so I'm going to explicitly write out the normalization. So we're going to take that moment of x minus mu squared, because it's a second moment, times that density, dx, normalized to the 0th moment, rho of x, dx. This defines the variance, the standard deviation. It's talking about how, if you're having a distribution that's centered on the average, how is the other data smeared around the average? So sigma squared is equal to the variance, where sigma itself is just the standard deviation. Standard deviation. One quick way that would convince yourself that this is the correct interpretation would be to take an example of a distribution. Maybe you have some rho of x equal to 1 over sigma exponential of, minus pi over sigma squared x minus mu squared. So this is just a Gaussian distribution. It just defines your little bell-shaped curve. And you can start taking these moments of this distribution and see if it agrees with what you already know about the distribution. If this is the variance and this is the average and this is your normalization, does this agree? So yeah, that's one way of kind of sanity checking what I've been telling you, is to actually pick a distribution and see if it agrees. So this is not providing you with rigorous proofs. I hope no one was expecting that. And we could keep going. So we could define the second moment, which describes the variance. We can describe a third moment, M3, properly normalized, which would give us the skewness. It starts to pick up the asymmetry of the distribution. So in other words, you can almost think of moments as allowing you to come up with crude approximations to the original distribution. If you only have the 0th in the first moment, then that's enough to define, the average. So you can put a little delta function centered at the average, and you can say, okay, maybe all of the data is here. But if you go to higher order moments that aren't 0, that's telling you deviations from that average. So you're going from something that looks more like a delta function to something that looks more like a Gaussian if it has a standard deviation. And then the skewness, looking at higher order moments, well, the Gaussian is a symmetric distribution. If you were to plot it like this, the left-hand side should look equal to the right-hand side if we were to kind of reflect the axes. But if that's not the case, maybe it's not symmetric, then the skewness would start to pick up on that asymmetry. And higher order moments in physics will tend to tell you things like angular dependence of the distribution, which is exactly quantifying how asymmetric it might be. So that's a really quick crash course into moments. The 0th moment, sum of parts. First moment gives us an average. Second gives us deviation from the average if we're talking about central moments. Third gives us skewness. We're not really going to be talking about higher order moments in this series, but just so that you know, that's what that would be interpreted into. And you can talk about higher order from that, like kurtosis. In the next video, we're going to be talking about moments of the mass distribution. So what we're going to do is we're going to come up with some hypothetical distribution of point particles. We're going to take moments of it, which should have something to do with things like center of mass, moments of inertia, and we're going to see if we can connect the dots back to these statistical interpretations. In the third video, We'll talk about the fact that charge densities kind of ruin things that we're talking about here, or they almost do. And that's because charge can be negative, which means this normalization, which would correspond to something like a total charge, would be 0. So it's going to be a lot more challenging to think of moments of charge distributions in terms of averages and standard deviations when we talk about the multipole expansion. So please let me know in the comments section if anything when we get to E&M you would really, really like to see, because there's no shortage of what we could talk about. I hope this has been a helpful little primer on statistics and the delta function, and I'll see you probably not next week, but the week after that for a part 2. So thank you guys for watching. Hope you enjoyed the video. Let me know in the comments section if you did. I'll see you guys there.